Assalamualaikum and a very good day to everyone. So today we will continue to the next chapter after capacitance, which is regarding on the Laplace and Poisson's equations, and where inside this equation we're going to look at the uniqueness theorem and the equations of Laplace and Poisson's equation. So this chapter will going to be the last chapter for electrostatic field, and after this we're going to go to magnetostatic field. Now let's look at the objectives and motivations for this chapter. So in this chapter you should understand the concept of uniqueness theorem, and you should also able to calculate the electric potential or electric field at a given point using the solution of Poisson's and Laplace equations. So previously we have learned that in order to measure the electric field or electric potential, we have been introduced to the E is equals to negative carats of V, alright, or V is equals to negative integrations E dot dl. So this is what we have learned in previous chapter, but now we would like to obtain the V by using the Poisson's and Laplace equations. Okay, so if you look at this slide, this is like a brief summary of what we have learned previously. Okay, methods to find electric field, where you has been given a charge distribution. You know there are 4 types of charge distribution. It can be a point charge, it can be line charge, it can be surface charge, or it can be a volume charge. And from this charge distribution, we have learned in chapter number 2 how to find the electric field using the Coulomb's law. And in chapter 3 we also have learned about the Gauss law, how to find the electric field, which simplest way by using a Gauss law. But in order to use the Gauss law, there is conditions that you should identify, okay, where you have to make sure that the material or the charge distribution is a symmetry, it is infinite line or infinite surface, or the structure is a spherical. Okay, and also we have learned from the charge distribution how to measure the electric potential. Okay, how to measure the electric potential, and from here also we have learned how to obtain the potential gradient, okay, by using the previous equation. Okay, E is equals to carat V, negative carat V, and also we have learned how from the potential gradient how to obtain the the other way around, how to obtain the electric field. Okay, so in this chapter, okay, we're going to learn about the uniqueness theorem, okay, where there are 2 properties or 2 conditions that you need to look, which is the area of the properties and the boundary of the conditions, and where both of this, okay, under uniqueness theorem there are 2 equations, okay, where later on we're going to look about the Poisson's and about the Laplace equation. But remember, please remember or bear in your mind that the Laplace that we have that we will learn in EMT, okay, Laplace law is a Laplace law, and it is not same with the Laplace transform that we have learned, or we have know this during our signal and system course. Okay, so our Laplace law in EMT is totally different with Laplace transform that we have learned in signal and system. So now let's look what is a uniqueness theorem. Okay, so a uniqueness theorem is a solution, okay, it's a solution to Poisson's or Laplace equation that satisfy the given boundary, okay, that satisfy the given boundary condition. And we said this equation is unique, okay, because this is the only and the one and only solution in order to solve the problem. Okay, so we said the solution is unique because the solution is only one, and that is the only solution in order to solve that particular problem. Okay, so the solution for electrostatic problem in electric potential can be unique for a specific region if uniqueness theorem is obeyed. So how to know either the uniqueness theorem is able to obey or not? You need to look at the boundary conditions. Okay, first you need to know the boundary conditions and also the area of the properties. Okay, so usually is from the area of the properties we can determine either the suitable problem is able to use Poisson's or Laplace equation. Alright. Okay, now let's look or let's recall the first Maxwell equation that we have learned before. Okay, I believe when you look at this equation, you are able to recall or you are able to know that this equation is our first Maxwell equation, which is divergence of D is equals to rho V, and this is our first Maxwell, Maxwell equation. Alright, and we have learned before, that this D can be substituted based on the Gauss law that we have learned, where D is equals to epsilon E. Okay, D is equals to epsilon E, and by considering, before that, you need to know or you need to realize that this is epsilon. This is not epsilon naught. Why? Because we want to know, because we are learning about the boundary conditions. Okay, so our material is no longer in a free space. Okay, it can be in different material. Okay, so if it is in a free space, it's gonna be epsilon naught, but in other material, it's gonna be as you're going to return as epsilon. All right, so now we have to consider that the whole material, we have a one material now, and this material is given as epsilon. All right, and we need to consider that this particular material is a homogeneous material. So what is a homogeneous material? Homogeneous material is a material that the whole particular structure is a uniform. The material is a uniform, and therefore the value of this epsilon is uniform as well for this whole structure. Okay, it is only one type of material. Okay, so let's consider that this material is a homogeneous material, so that we can bring this epsilon in front. Okay, and from here, okay, the E here we have learned in our previous chapter, okay, where E is equals to negative garage of V. Okay, so if we substitute inside that, it's gonna look as such. Okay, so now we have epsilon divergence dot negative garage of V is equals to this rho V. Okay, and if we do the mathematical arrangement, okay, if we bring this epsilon to the other side, to the right hand side, now we're gonna have two garage here. Okay, garage squared here, which is known as a Laplacian operator. Okay, it is known as a Laplacian operator. Laplacian operator is equals to negative rho V over epsilon, and this equation, okay, this equation is known as Poisson's equation, where inside that particular region of material, it has a rho V. Okay, it has a rho V, and it will if we divide with the material permittivity, okay, it can be a Poisson's equations. All right, it can be a Poisson's equation. However, if that particular region or this particular material doesn't have a charge of rho v, the value of the rho v is equals to 0, so that your Laplacian operator now, it will become 0 because the rho v is become 0. So this equation is known as Laplace equation, alright? And if the rho v is not equals to 0, it is known as a Poisson's equation. So to determine or to distinguish between Poisson's equation and Laplace equation, you need to look at the rho v. If the rho v has a value, it will be a Poisson's equation, and if the rho v is equals to 0, it will be a Laplace equation. Alright, so if you look at this equation, both of this equation, it has a Laplacian operator. Okay, this is what we call a Laplacian operator. So same as what we have learned in this formula, and also and also the divergence formula. This operator, Laplacian operator, is depending on the coordinates, orthogonal coordinate system. Alright. So it is going to be different for Cartesian, it's going to be different with a spherical, and it will be different for cylindrical. But you don't have to worry, all of that will going to be given to you. Okay, the formula will be given to you. Okay, so now let's assume that we want to determine, or we want to obtain the electric potential V, alright, in one particular material. So in order to obtain that, we can solve by using either Laplace equation or Poisson's equation. So you have how to determine this, how to decide which equation you want to use. You have to look at the value of rho v. So for example, in this case, for Laplacian equation, okay, so we assume that the rho v now is equals to 0. So we are able to use the Laplace equation. And based from the Laplacian operator, it depends on the coordinate system. So let's assume the coordinate system to be Cartesian. So this is a Cartesian, okay? And in Cartesian, we have variables of x, y, and z. So it's going to be double differential, okay, of v over dx squared plus double differential v over dy squared plus double differential of v over dz squared. So we're going to have three particular dimension. But okay, in this courses, okay, at your level of stage, we are only interested in solving only one dimensional problem, meaning that we will only interested in only one variables only. So it will be mentioned to you guys, yeah, which variables that you need to calculate. Right, so this is to make your calculation become easier and less complicated. Okay, so for example, if you are interested, or if the question asks you to find in x element, so it will gonna be double differentials of v over dx squared straight away equals to 0, or if it is request for y element or z element, it will gonna look as such. All right. Okay, so now let's assume that our interested variables, now we want to find v in x direction. Okay, we want to find v in x direction, and usually it can be written as such, yeah? Vx equals to what? So we want to get the equation, we want to get the general equation in order to find v in x direction. So we choose only x, or only x variable. So the equation we're going to be double integrations of v over dx squared is equals to 0. And since that it is double differential, so in order to obtain v, we have to use the reverse mathematical. So differential, the reverse of it, it's going to be integration. So it will be double integration. So the first integrations for this equation, it's going to be dv over dx, where it will be equals to a. And for the second integrations, okay, it will be dv of for the second integration, we will able to obtain the v. So therefore the v is equals to ax plus b. Okay, so a and b is a unknown. Okay, A and B is a variables that is unknown. So in order to obtain the value of A and B, it can be found or it can be solved by using the given boundary conditions. Alright. So these variables A and B, in order to be calculated, you need to get the information that is given to you guys from the equation, from the questions. Okay, now let's look at the example 1. We have a parallel plate capacitor has a separations of 0.5 millimeter between plates, and a potential difference between plates is given as 50 volts. So if rho V is equals to 0 and the value of permittivity is equals to epsilon equals to 4 epsilon naught between plates, find the Vy. Okay, between this range, if the potential at y is equals to 0 is given as 25 and y is equals to 0.5 millimeter, the value will be 75 volts. Okay, so now first of all we need to determine either we are able to use Poisson's or Laplace. Okay, so in this case, they mentioned to you guys that the value of rho V is equals to 0. So therefore, the equation that we're going to use is a Laplace equation. Okay, so since that the rho V is equals to 0, so we are able to use the Laplace. So therefore, okay, the Laplacian operator is equals to 0. And next, we need to know what is our interested variables. We want to know V in terms of what? In this question, they ask V in terms of Y. So by right, we can neglect the rest of other variables. So what are the orthogonal coordinate systems that suits with this problem? It's gonna be Cartesian, yeah, because it is a parallel plate. Okay, so it's gonna be V over dx squared plus dy squared plus dz squared is equals to 0. Okay, since our interested variable is equals to is in a y element, so this will automatically become a 0 and this will automatically become 0. This is only our interested part, yeah. So therefore, here it will be dy squared is equals to 0, and in order to obtain the V, we need to do the double integration. So the first integrations, it will give to us dv over dy is equals to a, right? So second integration, it will give us V, yeah, is equals to a at ay, because we are in y element, plus b, right? So usually the V is written as such, yeah, because we are interested in y element, V in terms of y element. All right. So now we need to obtain the A and B, the unknown of A and B. All right. Oh, I forgot to illustrate the structure. So the structure now, since that we are interested in y element, so it's going to be in y axis. Okay. And we have two parallel plates. So the first plate is located at separation is 0.5, 0.5 millimeter. So let's assume the second plate is the bottom plate is located at y is equals to 0, and the next plate is located at 0.5 mm. Okay, so therefore the separations of this will give us 0.5 mm distance, yeah. And then what else? The information that we get from the questions, they said that the permittivity is equals to epsilon is equals to 4 epsilon naught. Okay, 4 epsilon naught, and the difference between these two plates, okay, the potential difference between two plates is given as 50 volts. And based from the questions, they said at y is equals to 0, So this is our y is equals to 0. The value of volts is given as 25 volts and y is equals at 0.5 mm. The value of the voltage is given as 75 volts. So 75 volts minus 25 volts, it will give us 50 volts of voltage potential difference. Alright. So now based from the equation and the informations of this information, okay, we are able to find the A and B. So at y is equals to 0, the value of a V is equals to 25, and when y is equals to 0.55, the value of V is equals to 75. Okay, 75 and 5. So what we have to do, we need to do the mathematical way. So when your y is equals to, when our y is equals to 0, okay, when our y is equals to 0, the voltage is equals to 25, right? So the voltage is equals to 25. Our y is equals to 0 plus b. So this is our general equation. So based from this information, we can substitute inside this equation in order to determine the unknown variables here. So therefore, from here we are able to obtain our our b is equals to 25, right? So now once we know our b, okay, we can obtain our a. Alright, so 75 when y is equals to 0.5 mm, our voltage is equals to 25. So A is equals to, the y is equals to 0.5 times 10 to the power of negative 3 because it is in millimeter. Okay, plus B is equals to 25, right? So from here we can obtain our A is equals to 1 times 10 to the power of 5. So now we can replace or we can substitute these unknown variables inside this general equation. So therefore your Vy is equals to what is it, 1 multiply with 10 to the power of 5 in y plus 25. So these were gonna be your V equation, the potential equation for the range of 0 until 0.55 millimeter. Okay. Next question B, the electric field between plates. So the electric field between plates, we need to use this equation. E is equals to negative of V, Garrett V. Okay, so therefore this equation is gonna be dV over dy, alright, in y, because our interested point is on y element, so it will become equals to 1 times 10 to the power of 5 in negative y direction. Okay, volt per meter. Okay, don't forget to write the volt per meter unit, yeah. And then for C, they ask about the capacitance per square meter. So the capacitance for square meter C is equals to Q over V. Alright, so Q can be calculated by knowing the how much charge, right? Rho S on the ds. And V is equals to the potential difference. So the potential difference has been given to you guys, which is 50. So straight away 50. So C will become, okay, but then the question asks capacitance per square meter. Yeah, square meter can be known. So if you know the integrations of ds, you will get the square meter, right? So we can put this because capacitance per square meter. So capacitance per square meter, ds, ds. So rho s you divided with 50. Okay, rho s is divided with 50. So rho s can be determined how? Can we determine this rho s? Yes, right? We can determine this rho s based on our previous boundary conditions that we have learned before, where E is equals to rho s over epsilon rho s over epsilon, right? And the E we have determined earlier in question number B, so we can say we can substitute here 1 times 10 to the power of I don't have space to write, so allow me to erase some of the writing here so that I have space to write. Okay, so E that we have calculated in question number B, 1 times 10 to the power of -5 in negative y direction, right? So equals to our rho s and epsilon naught. So the charge also will follow the the directions of E field, right? Negative y. So the directions of negative y can be cancelled, all right? Oh, this is not epsilon naught, this is only epsilon, right? So this is epsilon. So epsilon is equals to 4 epsilon naught. So you substitute inside here. So you are able to know the value of rho s. Okay. So you will get coulomb per, capacitor per meter square. It's gonna be 4 times 10 to the power of 5 epsilon naught over 50. Okay, over 50. So please calculate this, come up with one value. So the value will gonna be in the unit will gonna be in farad per meter squared, yeah, because it is capacitor per meter squared. Okay, now let's look at the example number 2. Okay, so for example number 2, there are two infinite length concentric and conducting cylinder of radius RA is equals to 0.02 meter and RB 0.05 meter are located with axis on the z axis. Okay, if epsilon is equals to 4 epsilon naught as well and rho v is equals to 0, so straight away we are able to use Laplacian, yeah. Between the cylinders, V is equals to 50 volts at RA and V is equals to 100 volt at RB. We need to find the range V in the range of 0.02 in R direction, 0.02 radius until 0.05 radius. Okay, so we know the V that our interested is in R direction. V in R direction. So if you can illustrate the structure will gonna look like, okay, so this is the first cylinder and this is other cylinder. Okay, so the first cylinder is given as RA. The next cylinder is given as RB. Okay, so the first cylinder inside here is rho V is equals to 0. Okay, and what else? The epsilon is equals to 4 epsilon naught. Then what else? So this is the cylinder, yeah. And then the next one is the cylinder at RA is given as 50 volts. The RB cylinder is given as 100 volt. So we need to find the potential. Alright, so first we need to identify the orthogonal coordinate system. So straight away we can know that the orthogonal coordinate system in this case we're going to be the cylinder and the variable is R, phi and z, but then we only interested in R. So based on our Laplacian, okay, based on the Laplacian formula for the cylinder in R direction or in R element, it will be, okay, the A, it will be 1 over R dv over dr R dv over dr is equals to 0. So the first integrations of this equation, because we need to obtain the value of V, so the first integration we are able to obtain R dv over dr is equals to is equals to A. Okay, is equals to A, and So therefore, dv over dr, it will become A over R. Okay, it will become A over R. And then second integration. Okay, so in second integrations of this, we are able to obtain VR is equals to A ln R plus B. Okay, so these are going to be the general equations that only true for this case. So this is what we said about the uniqueness theorem. Yeah, this general equation is only true for this case only. All right. So we want to put the A and B variables. So based from the equation, from the information from these questions, when your AR is equals to 0.02, okay, the value of V is 50 volts, and when your R is equals to 0.05, your V is equals to 100. So if you substitute inside this general equation, you will get, or you're supposed to get the equations to be VR is equals to 54.56 ln R plus 263.4 volts. Okay, right? So for B, same as previously. For B, so in order to determine the E, okay, you need to do the E is equals to negative karat of V. Alright, so you are able to obtain or you should obtain where the value is equals to 54.56 divided with R in negative R direction. Okay, volt per meter. Okay, so for C, you need to determine the electric flux density. So it is D is equals to epsilon E. Okay, D is equals to epsilon E. So this one I leave it to you guys. You can do by yourself. Okay, epsilon is equals to 4 epsilon naught multiply with the E that we have obtained earlier. Alright, so D. So for D, we need to determine the rho S at RB. Our interested part is rho S at RB. So this is our RB. We want to know the rho S. So the E that we have obtained earlier, 54.56 over R in negative R direction. Okay. Okay, so we're going to use the equations of same as previously, the boundary equation, rho S divided with epsilon. So the E is 54.56 and our R is our RB because we are interested in RB. So RB is equals to 0.05. Okay, equals to rho S, and our epsilon is 4 epsilon naught. Okay, and from here we are able to obtain our rho S. Okay, you should be able to obtain the rho S. Okay, and remember that this rho S is rho S that is located at RB. Okay, right, so please allow me to erase some of writings here so that I can have a space to write for E. Okay, so this, erase this here. Okay, so now I have some spaces, and so this is the answer for E. Alright. So for E, we need to determine the capacitance per meter length. So meaning that C over L, so capacitance per meter length, right? So C is given as Q divided with V. Okay, same as previously. Q is rho S ds, and V will gonna be the potential difference. So potential difference you have to minus lah, 100 volt minus with 50 volts. So it will gonna be 50 volts. Okay, and see, yeah. Alright. So rho S you have calculated earlier. So the rho S that we have calculated in this question D, so it's gonna be 4 epsilon naught 54.56 divided with 0.05. Okay, ds, integrations of ds for cylinder is gonna be L, the length of the cylinder. So we assume the cylinder, the length is L because we don't know here the value. L 2 pi and 2 pi r, right? Rho S ds, is it? For cylinder, it's gonna be 2 pi L r. So L is gonna be the length for cylinder. R is R. Which R that we should choose? R of RA or R for RB. So we have to look back the rho S. So the rho S that we are taken is RB, right? 0.05. So your R should be 0.05 because our RB is 0.05. Sorry, our rho S is at RB, yeah? Divided with 50. So they want capacitance per meter length. So therefore, okay, I have to erase this as well. Yeah, I thought I can just leave that, but I have to erase. Okay, so it's gonna be C over L. So this can be cancelled to each other. So it will be 4 epsilon naught 54.56 divided with multiply with 2 pi divided with 50, and this is going to be farad per meter. Alright, okay guys, so that's all for this lecture. So for our next lecture, which is after your mid-sem, it's going to be the magnetostatic field and sources, and also we're going to learn about the Biot-Savart's law. So I will be appreciate if you guys can have your early learning or early reading, for these two topics. So thank you so much guys, and see you for the next class.